Okay, this is my presentation on elephant toothpaste for Module 6, Critical Thinking. Okay, so here I have all of the things I needed for this experiment. So I got active dry yeast. I actually did the experiment in this cup. On second thought, I wish I did it out of a bottle. I think it would have looked cooler. I have food dye. I used blue. Hydrogen peroxide, I could only find 3%. I know if I used 10%, it would have been more explosive. And then this is my dish soap dispenser, so I just put some drops in there. All right, so I'm gonna play. And I mix the yeast with warm water. Didn't say how much to use, so I just kind of poured a little bit in and watched it bubble out. So you can see there's bubbles there that suggests that a gas was formed, which we'll get into later with the questions. But it did come out like a nice toothpastey looking consistency. It was really more foamy. But yeah, I could have done some more food dye to make it look a little bit cooler. And again, if I used more of a bottle-like, that would have been better because the cup didn't really do it all that well. All right. All right. What was the overall reaction? So the overall reaction was exothermic, and we know this because the cup was hot afterwards, so when I felt it, it was pretty warm, which I was kind of surprised by. I didn't think it would get that warm. And then more specifically, it is a decomposition reaction because hydrogen peroxide decomposes into water and oxygen. And then the chemical reaction would look like this. So we have hydrogen peroxide aqueous, turns into liquid water and gas oxygen. The kinetics of this reaction. So this was a really fast reaction. Once I added the yeast that was mixed with the warm water or the catalyst, it went very quickly. So the catalase was the name of the catalyst, and that speeds up the reaction quickly, breaking apart the oxygen from the hydrogen peroxide. The speed of the reaction created a lot of gas bubbles, which were filled with oxygen. This was an exothermic reaction, so heat was also generated. Rate increases as temperature increases, and increasing the concentration of reactants would also increase the rate of this reaction. Okay, thermodynamics of this reaction, including Gibbs free energy and spontaneity. So an exothermic reaction, like I've said before, is a process that releases energy in the form of heat, and the thermodynamic analysis of such reactions involves the concept of Gibbs free energy, delta G. Gibbs free energy is a thermodynamic function that measures the maximum amount of useful work that can be obtained from a chemical reaction under constant temperature and pressure conditions. For an exothermic reaction, the change in enthalpy is negative, indicating that the energy is being released to the surroundings. The entropy of the system may increase or decrease depending on the specific reaction. The Gibbs free energy change for an exothermic reaction is given by the following equation. T is the temperature in Kelvin. The negative value of delta H contributes to a negative delta G, making the reaction spontaneous in the forward direction at a given temperature. At a constant temperature, a negative change in G indicates that the reaction is spontaneous in the forward direction, meaning that it will occur without any external input of energy. Conversely, a positive delta G indicates that the reaction is non-spontaneous in the forward direction and requires an external energy input to proceed. So overall, the thermodynamics of an exothermic reaction can be analyzed using the concept of Gibbs free energy, which is going to help us determine the spontaneity and extent of the reaction. Okay, and then we'll talk about the catalyst used in this reaction. So yeast acts as a catalyst to speed up the elephant toothpaste reaction. Catalase breaks down hydrogen peroxide into oxygen gas and water. The oxygen enters the soap bubbles that we added in with the dish soap, causing the substance to quickly expand out of its container and overflow, creating the elephant toothpaste. The The catalyst is homogeneous because both the reactants and the catalyst are always in the same phase. How could we test that a gas is produced? So we can test this just by carrying out the reaction and observing the appearance of the reaction. So once we perform the reaction, we can obviously see that bubbles are formed, and we also see a color change, which are both indicators that a gas was produced. The foam produced is a result of oxygen-filled bubbles from the hydrogen peroxide being broken to water and oxygen. So those bubbles are filled with oxygen. And that's it. Thanks.